Viewed from Earth's orbit, Palm Jumeirah emerges as a proud scar carved by humanity into the ocean. To comprehend this audacity, we must travel back to the late 20th century, a time when the Al Maktoum dynasty forced strange trips. A dwindling economic lifeline forced Dubai to reinvent itself, attempting a radical metamorphosis to become the Dubai's natural coastline at the time spanned a mere 72 kilometers. It was far too short, too narrow, to anchor mega-resort projects. It was at this pivotal moment that Dubai's leadership embraced an audacious vision. If natural land was limited, the initial response from international engineering firms was conventional, to construct fixed, massive, reinforced concrete viaducts resting on deep bored piles driven into the Gulf floor. However, the king instantly rejected the blueprint. He demanded that the island be real land, a completely natural structure of sand. This uncompromising decree threw contractors into a severe crisis of thought, building a mega-island out of nothing but raw, loose elements. And so, a project unprecedented in human history was officially set in motion, initiating a fierce, decade-long war.
Pouring sand to build an island sounds like child's play on paper, until engineers step onto the field and encounter the treacherous, unpredictable current night of it. This region frequently endures the ferocity of Shamal storms, carrying extreme, blinding winds capable of swings.
Furthermore, deep subsurface surveys revealed a fatal geological hazard. The seabed geology in the plan zone consisted.
Any massive static load placed prematurely on this surface would instantly trigger natural sliding and subsidence. Marine geologists had to spend grueling months accurately measuring and locating the solid bedrock structure, buried tens of meters beneath that shifting mud layer. They had to map wave energy mathematically, translating chaotic oceanic patterns into precise equations to calculate the frequency. Any error in this marine geodesy phase would mean absolute financial ruin. The analytical data quickly proved that without a heavily fortified protective barrier against continuous erosion, the island would. Therefore, the primary mission was not to build land, but to challenge the marine currents by engineering a protective breakwater marvel like no other on Earth. Inside the renowned hydrodynamic laboratories in the Netherlands, supercomputers were tasked with simulating a lethal scenario. The simulation revealed a critical flaw. If a completely solid, enclosed circular breakwater ring were constructed, the immediate consequence would be stagnant seawater trapped inside the small bays, wiping out the oxygen levels required to sustain a living marine ecosystem. This stagnant, unmoving water would turn the luxury island into a foul, stinking swamp with its weeks. Refusing to accept defeat, engineers scrapped the old model and initiated hundreds of physical, rigorous tests inside massive, state-of-the-art wave-generating tanks. It was during these trials that a revolutionary architectural solution emerged. Instead of a closed circle, they decided to slice the outer breakwater. These strategic, hundreds of meters wide gaps were designed to harness natural tidal pressure, creating a highly efficient, automated suction effect. This precise mechanical arrangement forces the entire internal water volume to automatically circulate, completely refreshing. With the complex hydrodynamic equation finally solved on paper, the engineering team cleared the path to manifest this megastructure out in the open ocean. In the year 2001, the great maritime construction officially commenced. The most brutal phase was erecting the 11. Rejecting prefabricated concrete blocks, the design utilized layers upon layers of raw, natural quarry rocks, with individual. These rocks were meticulously interlocked by heavy cranes, intentionally creating natural microgaps to absorb, fragment, and disintegrate the sheer.
Once the breakwater took shape, a massive fleet of specialized trailing suction hopper dredgers arrived, initiating the historic and spectacular rainbowing technique.
But a staggering puzzle emerged out on the water. How could these isolated ships shape a perfectly symmetrical palm structure from kilometers away?
To
To achieve flawless, absolute perfection, the project synchronized its operations with an elite asset.
Spatial coordinates from orbit were constantly fed to shipboard workstations, automatically adjusting the vessel's mooring lines and blasting angles down to the millimeter.
Every single day, tens of thousands of cubic meters of ocean sand were precisely arranged by these invisible hands, navigating from Earth's orbit. Looking down from the skies, the silhouette of a colossal sand creature gradually materialized, permanently shattering the timeless solitude of the sea. The moment the island's geometry was finalized, a rigorous geological quality audit was initiated on the newly artificial ground without delay. The mechanical testing revealed a terrifying reality. The newly rainbowed sand was extraordinarily porous, loose, and trapped massive pockets of air and water. This phenomenon is defined by geologists as soil liquefaction, a literal, subterranean ticking time bomb hidden directly underneath the foundation of the island. Located uncomfortably close to the active seismic trigger zone of the Iranian fault line, even a minor tremor traveling through the ocean bed could spark total catastrophe. Dubai's newly created ground would instantaneously liquefy into a shifting river of mud, dragging all upper superstructures and palaces into the deep ocean abyss. To tame this treacherous, loose sand layer, engineers deployed an aggressive engineering response. Deep Vibroflotation technology on an industrial scale. Colossal mechanical probes were driven tens of meters deep into the sand, broadcasting acoustic shockwaves at intense, bone-rattling frequencies. This violent vibration forced the loose sand grains to lock tightly together, aggressively expelling trapped air and deep-seated water upward to the surface.
This structural compaction process successfully densified the ground, transmuting the loose island into a solid rock-like
Thousands of subsequent static load tests simultaneously flashed green across the grid. The island's foundation was now verified as safe to support towering skyscrapers.
In 2006, the first residents officially moved in, transforming a man-made desert in the ocean into the ultimate.
International architecture critics and journalists from prestigious publications like Architectural Digest and National Geographic stood astounded by the real-world results.
Global media ran continuous, breathless coverage, honoring the engineered marvel of Palm Jumeirah as the unofficial eighth wonder of the modern world.
Against all odds, Dubai had successfully extended its luxury coastline by 56 kilometers, generating infinite layout options for high-end resort hospitals. The ultimate crown jewel of this achievement was the rise of Atlantis the Palm, a legendary architectural icon ruling over the absolute apex of the crescents. The project did not just modify the physical topography of the Emirates. It completely realigned Dubai's economy. Yet, an empire born from sand will eternally be targeted by the ocean. The battle to maintain its structural integrity is an endless, silent war. Every single day, maintenance engineers must continuously monitor underwater erosion, actively attacking the deep foundation of the rock breakwater. Subsurface sonar networks scan the perimeter 24/7, mapping the slightest shifting of the 6-ton rock blocks under the relentless assault of marine currents. Furthermore, the realities of modern climate change and 21st century sea level rise scenarios are presenting the island with a raw, continuous test of survival. Today, Palm Jumeirah is no longer seen as a pure symbol of luxury. It has evolved into a vital node. It stands as definitive, majestic proof that when sharp journalistic vision meets peak engineering,